Hello students, I welcome you all to the online video lecture on course Heat Transfer, the module number 5, chapter 2, that is boiling and condensation. This is the ninth lecture on boiling and condensation. In the today's session, we will study the numericals on the condensation which has been asked in the previous year examination. Let's read the problem carefully now. A vertical plate 500 mm height and maintained at 30 degrees centigrades is exposed to saturated steam at atmospheric pressure. Calculate the following: rate of heat transfer, that is Q, capital Q. And the second bit is the condensation rate per hour per meter of plate width for film condensation. The second bit, we need to calculate the value of m dot, that is the condensation rate per hour per meter width of the plate. Okay, now let's write down the given data. Height of the vertical plate, which is designated by capital L, that is 500 mm or 0.5 meters. The surface temperature of the plate, that is Ts equals to 30 degrees centigrades. Now the temperature of saturated steam at atmospheric pressure Tsat equals to 100 degrees centigrades. As he has not given this 100 degrees centigrades, as I told you in the previous lecture also, whenever he gives the steam at atmospheric pressure, then we supposed to take the saturation temperature as 100 degrees centigrades. Okay. Now in the condensation, we have to extract the thermophysical properties of water at mean film temperature. Okay. So the mean film temperature is the Ts plus Tsat divided by 2. You have to take the average of these two temperatures. So you'll get 65 degrees centigrades as mean film temperature. Next, at this particular temperature, we have to take the thermophysical properties of liquid at the film temperature, the mean film temperature. Now refer the page number 21 of your data handbook to take the properties of water or the condensate at mean film temperature. So let us refer the data handbook here. Let us refer the data handbook, the page number 21. So you should be very careful while referring the data handbook. Okay, now this is a page number 21. This is a page number 21 for water. Now the mean film temperature is 65 degrees centigrades. 65 degree centigrades. But here we have the values at 60 degrees centigrades and 80 degrees centigrades. First take the average of these two. So value at 60 degrees centigrades plus value at 80 degrees centigrades divided by 2. So the average will give you the value of density at 70 degrees centigrades. So after you got the value at 70 degrees centigrades, that value plus the value at 60 degrees centigrades, take its average, you will get the value at 65 degrees centigrades. I repeat, add these two, divide by 2, you will get value at 70 degrees centigrades. The 70 degree value plus 60 degrees centigrades value, add these two and divide by 2, you will get the value at 65 degrees centigrades. In similar way, take the value of density, take the value of the kinematic viscosity nu, and lastly take the value of K in similar way. Okay, so I got the values at 65 degrees centigrade, the thermophysical properties, that is density of liquid 982.25 kg per meter cube. Next, nu equals to 0.4495 into 10 to the power minus 6 meter square per second, and the thermal conductivity of liquid is 0.6556 watt per meter degree centigrades. Okay, now as I told you in the last problems also, take the enthalpy value, that is HFG value, mandatorily at 100 degrees centigrades. Except this value, except this HFG value, take all the properties at mean film temperature. Okay, I repeat, do take the enthalpy value at 100 degrees centigrades, that is Tsat equals to 100 degrees centigrades. Okay, but all the other thermophysical properties that should be taken at mean film temperature. So please keep it in mind. Fine. Now let's go to the first bit, the rate of heat transfer per meter width. The rate of heat transfer per meter width, that is Q. Now we know the formula for film condensation. For film condensation for laminar flow on vertical surfaces, the H value, the average heat transfer coefficient, is given by, so let us refer the data handbook, the page number 148, the page number 148. Okay, well students, this is on the next page, I guess. Okay, fine. This is for condensation, the film wise condensation on vertical surfaces. This is on vertical surfaces. Okay, now this value of H is a heat transfer coefficient for laminar flow. Film wise condensation for laminar flow, the value of average heat transfer coefficient H equals to 0.943. H equals to 0.943 into this complete parameters raised to 0.25, raised to 0.25. Okay, now here TV is a temperature of vapor, or it is also known as the Tsat. Both are same. TV, you can take TV or you can take Tsat. Both are same. So Tsat, the saturation temperature, minus the surface temperature. Okay, fine. So don't take this equation, because this equation is applicable for horizontal tubes. This equation is for horizontal tube, and this equation is for the vertical surfaces, the vertical surfaces. So you can ask why we are not using this equation, because this equation is for the thickness of the condensate film, the thickness of condensate film. So if you substitute the delta X in this equation, and after simplification, you'll get the value of HL, and after substituting the value of HL in this formula, you'll get H equals to this complete formula. Okay, after substitution you will get the same formula, but here he has not asked to calculate the delta X, that is thickness. Directly he has asked to calculate the rate of heat transfer, so for which we need the value of H, that is average heat transfer coefficient. So directly you can use this equation. Fine. Okay, now let me clear you that this equation is for the laminar wavy free flow, the laminar wave free flow, where the Reynolds number is less than 30, where the Reynolds number is less than 30. Okay, this will be more clear if you solve the numerical further. Okay, anyway, let us use this equation first. Let us use this equation first. Okay, now H equals to 0.943 into the bracket raised to 0.25, 0.25. So substitute all the values and do the calculation precisely. You'll get the value of H as 4189.30 watt per meter square kelvins. So this is a value of average heat transfer coefficient. Now the rate of heat transfer is given by Q equals to, use the Newton's law, Q equals to HA into Tsat minus Ts. Okay, Tsat minus Ts. So substitute all the values, because he has given the vertical plate, the dimensions of vertical plate, a height is 500 mm and the width is 1. The width is 1 meter. See, read the problem carefully. The plate per width, per unit width. Okay, so do take the width equals to 1 and this is the height. So height into width is the area. So substitute all the values and the expected answer for Q is the rate of heat transfer, that is 14,000 okay, 146625.7 watt per meter width. Now the rate of condensation is m dot equals to Q by HFG. m dot equals to q by hfg. Q is the rate of heat transfer. The hfg is the enthalpy of evaporation or enthalpy of vaporization. That is 0.065 kgs per second. You know the value of q, just now you have calculated. You know the value of hfg, just substitute and get the value of m dot, that is rate of condensation. Now a Reynolds number is given by, so why we have to take the Reynolds number here? Check in which regime it is existing. So initially what we have assumed, the flow is, initially what we have assumed, so initially we have assumed that the flow is laminar wave free, when Reynolds number is less than 30, less than 30. Okay, now we have to prove now. Okay, yes, our assumption is correct. So let us find out the value of Reynolds number. So if you find out the value of Reynolds number, that is 4 m dot divided by mu suffix l into b. You got the value of m dot. You know the value of mu l. So how to get the value of mu l? Just multiply the density and the kinematic viscosity. The product of these two values will give you mu, that is absolute viscosity. Okay, width b is equals to 1, that is known. Okay, so after calculating the value of re, the expected value is 558.58. This is the value of re, and obviously this value of re is more than 30. So what we assume that the flow is laminar wave free is wrong, because we are getting the Reynolds number more than 30, more than 30. So this is the region, this is of course the second region where the flow is laminar wavy, laminar wavy. So please refer this figure. So for Reynolds number more than 30, the region is laminar wavy, and we have proved that in the last class also. We have seen that the rate of heat transfer in wavy laminar flow is 20% more than, is 20% more than what we have in laminar wave free region. Okay, so that's why the assumption made by us initially is wrong, because the Reynolds number is more than 30. Okay, so what we have to do, we have to multiply the rate of heat transfer q with 1.2, because 20% more, because in this region the rate of heat transfer is 20% more. Okay, fine. So here I have mentioned, as Reynolds number is more than 30, which indicates the flow is laminar wavy in nature. So use the McAdam correlation. So if we multiply the rate of heat transfer q with the 1.2, then it is nothing but the McAdams correlation. Okay, that is a McAdams approach or McAdams assumption. Fine. So the rate of heat transfer is 20% more in laminar wavy region. In laminar wavy region. So therefore, the rate of heat transfer is, just multiply with 1.2 here. Okay. So obtained value of Q is 146625.78. So just multiply with 1.2 here. Just multiply with 1.2. So you will get the value of Q as 175950.94 watt per meters. So now the rate of condensation, that is m dot, is q by hfg. Now q is changed. So substitute q equals to this value divided by hfg is already known to you. So take the hfg in terms of joules per kgs. Okay. So therefore 0.078 kgs per second per meter. Kgs per second per meter. Here you have to take kgs per second per meter, because width is equals to 1 meter. Width is equals to 1 meter. Okay. So these problems are very important from your examination point of view. See students, I have solved this problem in detail. So initially you can assume, okay, so initially you can assume the McAdams correlation, because in 99% of cases you will get Reynolds number more than 30 only. So here at the beginning only you can multiply this q with 1.2 and you can find out the value of Reynolds number. Okay, so no need to do the multiple steps. Just for understanding purpose, I have done the two separate steps. So in examination, directly in this step only you can multiply with 1.2 here, and after that calculate the value of Reynolds number. So you'll get the Reynolds number as, okay, so you'll get the Reynolds number as more than 30. Okay, so 99% of cases you will get Reynolds number more than 30 only. So instead of going to the multiple steps, here only you can multiply with 1.2. Okay, I hope this is clear. Now take this problem as the homework. The example number 5, which is asked in the previous year examination. So vertical flat plate in the form of fin is 600 mm in height and exposed to the steam at atmospheric pressure. If the surface of plate is maintained at 60 degrees centigrade, calculate the following. The first bit, the film thickness at the trailing edge of the film. The trailing edge of the film. So what do you mean by this trailing edge? This is our fin. This is our fin, the side view of the fin, which is having some thickness. This is a film. And when this fin is exposed to the saturated steam, when this film is exposed to the saturated steam, then a film is formed, a thin layer of film, the liquid condensate is formed. So what he's asking, the film thickness at the trailing edge, the last bottom edge, this is the trailing edge. So remember students, this edge, the starting, this edge is called leading edge. This edge is called leading edge, and the bottom edge is called trailing edge, the trailing edge. So here x equals to 0, x equals to 0, and here at the bottom x equals to L. Okay, so at this bottom you have to calculate the thickness of film, that is x equals to L. Already you know the equation which is given in the data handbook, so please go through it and calculate the value of delta x or delta L. Okay, after that substitute that delta L value in that equation. You will get the average or overall heat transfer coefficient, and after that calculate the value of heat transfer rate. Okay, here also at the beginning check the value of or the calculate the value of Reynolds number after getting the value of heat transfer rate. Okay, and check whether RE is greater than 30 or less than 30. If RE is less than 30, then the calculated or the approach is correct, the approach is right. But if the Reynolds number is more than 30, if the Reynolds number is more than 30, then you have to go with the McAdams correlation. Just multiply this rate of heat transfer Q with 1.2. That's it. Okay, the last bit, calculate the value of condensate mass flow rate, that is m dot. Okay, and here also we have to assume the laminar flow condition with the unit width of plate, that is b equals to 1. We have to assume b equals to 1 meter unit width. Okay, please solve this problem and put your answers in the comment box. Okay, so we'll end the today's session here itself. So please like the channel, share the channel, and subscribe the channel, and don't forget to press the bell icon so that whenever I post a new video on YouTube, you will get the notification instantly. Okay, so thank you, and have a nice day.